Hello and welcome back. We're going to be focusing on Mod Guide for Module 12 today. Deals a lot with linear relationships and correlation. It's going to continue what we've been talking about for Module 11. The Learn by Doing from page 68 asks us about an activity that we have that has 21 female college students where we're talking about forearm length in inches as the explanatory, which is our X variable, and then height in inches as the response, which is our Y variable. And the line is a good summary of the linear pattern for the data. It looks like it would have a strong R, or strong correlation coefficient. Based on the graph of this line, which is the best prediction of the height of a woman with a forearm of 11 inches. But what you're going to do is you're going to go down to forearm, which is on the x-axis, and you want to hit 11, which is the measurement that we're looking for. And you want to take 11 all the way up to the line, and that's what our prediction is going to be. So if you go to the left from that line to your y-axis, you can get an idea of what that y value should be. And it's bigger than 68 and less than 70, which means that it's going to be number 3, which is 68.75. It was just a little bit higher than 68, so it wasn't 68 exactly. Now the equation of this line is the predicted height is equal to 39 plus 2.7 times the forearm length. Use this equation to predict the height of a woman with a 10-inch forearm. So what we're going to do is we're going to say height, and when we use predicted, we can often use a hat. So you'll see y hat or height hat is equal to 39 plus 2.7 times 10. Well, that's 39 plus 27, which gets us 66 inches. You've probably heard of extrapolation in your day-to-day life. It has a specific meaning when we're talking in statistics, and it is the prediction for values of the explanatory that fall outside the range of data. So you're talking about making predictions for X that aren't in your range of X. For instance, if I go back to this original problem for forearms, I have forearm lengths from 8 inches to 12 inches. But if I was to ask you to make a prediction for something with a forearm less than 8 inches or greater than 12 inches, that would be considered extrapolation. And the reason is because when we're talking about the data range from 8 to 12, we don't know that the linear pattern continues less than 8 or greater than 12. The Learn by Doing, again from page 68, has this data set with X being the annual cigarette consumption per capita in the US and Y is the number of lung cancers per 100,000. And they want to investigate the connection between cigarette consumption and lung cancers, and it's offset by 30 years since cancer takes time to develop. For example, cigarette consumption in 1945 is paired with cancer rates from 1975. The cigarette consumption data from 1945 to 1975 is in 5-year increments. There's a strong positive linear association. Remember, strong, positive, and linear, those are the ways that we want to describe. We wanted to talk about strength, form, direction, and the outliers. The strong positive linear association between annual cigarette consumption and lung cancer rates. The correlation is 0.81, and remember, that's an R value of 0.81, which means it is strong. If we use the line to make predictions of the number of lung cancer deaths per 100,000 people, which of the following is an example of extrapolation? Remember that extrapolation is outside of our data range, and we have data values that are around 3,400 to 4,400. The 35 is in our range, that's not extrapolation, and 38 is also in our range. Here's 35, here's 38. Now 46 out here, this is considered extrapolation because it is outside the data range. Continuing on, the Learn by Doing from page 68, we've modeled the data using a curve instead of a line. So instead of using linear correlation, we're talking about curves. So compare the lung cancer rate predicted by the two models when the cigarette consumption is 3,200 cigarettes per person. Which one gives a reliable prediction? The 3,200 is right here on the graph. And for the curve, you're looking at about 28. And that's 28 per 100,000, so 2,800,000. And the line gives a prediction of about 44, so 4,400,000. But does either model give a good, reliable prediction? We don't know. We don't know what's happening below this value right here. This is considered extrapolation. So we can't really make a determination. This is outside our x values. Now let's look at question 5, where we're asked which line is better than the other. Now, what we're looking at here is we're looking at how the line fits the data. Now, remember, we want our data to be as close to possible as the line. We want, we're trying to minimize the sum of squares, which we'll talk about in a minute, but notice that these lines are pretty far away, or these points, but this other points are pretty close together. Whereas on the second line, we've got smaller lines overall. So I would say that this line is better because the data is all closer together. The line is closer to the 5 points rather than close to 3 and far away from 2. So it better summarizes the pattern better. So this is the better line. I mentioned the line with the sum of squares. So what that means is from each point that you have, you draw a square from the point down over, and then you calculate the area of each of these squares. And so you want the smallest sum of squares. So when your computer is calculating these values and they're trying to determine which line is best when they do a line of best fit, it's running through all of the different placements of the line to figure out which one creates the smallest sum of squares. So notice that the squares are larger on the left-hand side, but they're smaller over here, which again, this is the better line. This is a better fit. May not be the best fit, but it is a better fit. And we're going to investigate what it takes in terms of those values in our next video.